Before we go any further with the functions of several variables, having defined what a level curve is and then what a contour plot is, I thought it would be good to just spend a couple minutes giving you some examples, some more examples of these contour plots, and then let Maple do all the messy work of the plotting, and then we can just sit back and enjoy the results. So I have a few here already set up. Now, each of these are assumed to be in the explicit form. So the z value is equal to, in this case, 3x minus 2y. So if you think of that equation, it's all linear, right? So that would define a plane, and we're finding the contour plot of the plane z equals 3x minus 2y. So even though you don't see the z equals, it's assumed to be there. It's assumed that z is the independent variable. So let's take a look and see what this contour plot looks like. Remember, when we did it by hand, we got a bunch of parallel lines. Let's see if that holds. And those look like lines, and they do look parallel, right? And yeah, so those are the contours. Now, what's interesting about Maple is that if I wanted to know what is the value of z that corresponds to any one of these lines, I just have to hover over the line. So, for instance, it kind of snaps, it forms this grid, and then it kind of shows you. So the z value. So let me put it this way. So every point, every ordered pair on this line that it's kind of like snapped to this line. Every ordered pair on this line, if I were to evaluate it in this function, so if I were to put the x value there, the y value there, I would end up getting a z value of 2.27 approximately, right? If, however, I evaluated it at points on this line, I end up getting negative 2.27. Really interesting. So you go from a height of a positive 2.27 to a height of negative 2.27. So again, if you interpret this as like elevation above sea level, this would be roughly 2.27 units above. That's where you would be on the surface versus 2.27 units below. And then here, so the color scheme is this. You notice you're going essentially from red to blue. So the blue would be the coldest. So this would be the highest, as far as what you see here, this is the highest level at z equals 20.5. And then down here, you're really, really hot, and it's kind of on the opposite end of the spectrum at negative 20.5, right? So you're going from warm to cool, right? Let's see. So all the other ones are non-linear. So this one, 1/10. I have no idea why I chose 1/10. 1/10 x cubed minus y. That's your z. Let's look at these contours. Okay, so now we can start to see the curves, and again, you can see now the colder. Again, the coldest possible value for this window, this range of x and y, is 18.4, and then over here is it negative 18.4? Yes, yep. So there's kind of a symmetry here. Let's see this one. So we got an exponential function here. Okay, now these are interesting. Now these are not, obviously they're not circular, right? But it's for us to get these kinds of curves, it must be must be a really interesting equation. But again, these would be treated as implicit curves, right? Because these are technically not functions anymore, because they failed a vertical line test, right? So y can't be a function of x here. But yeah, so that's the contour. So you can see the warmer regions are here, and then it goes outward, and then all of a sudden it like flips over to this side, and then your z value continues to increase, right? So the largest z value along these contours that's attainable is roughly 0.348, right? All right, two more. See, what is this one? Oh, okay. So we have not super warm regions, but a negative, actually, yeah, negative 1.75. Yeah, so you can see it slowly increasing, and then now it's on the positive side, and then continues to increase that way. And again, these are not equations that will be easily plotted by hand, and that's why software like Maple is really useful. So let's see our final one. Yeah, I took the sine of 2x times the cosine of 3y, and that's being treated as the z value. So let's see what the contour plot for this one looks like. Oh wow, that is interesting. But not surprising though, when you think of the fact that your sine and cosine functions are periodic. So you end up seeing this kind of repetition, hot, cold, hot, cold, and that notice. So here I'm going vertically down, and then of course it's the same thing kind of happens when you go horizontally. Hot, cold, hot, cold, right? So really, really interesting contour plots, and you can use them to design really cool patterns. If you start playing around with them. But here again, I just wanted you to see, the different contours that can arise based on these different surfaces. So again, what we're plotting here is essentially all the or a set of cross sections of the surface, and we kind of open it up, look at what the curve looks like, and then we're just going to plot it, or in this case Maple is going to plot it in the xy plane, and a whole bunch of them together is what we call a contour. All right, so now that we have all those visuals in our head, it's time to get serious with some mathematics. So if you're up for that, hop on over to the next video. See you then. Bye.